Good morning. Welcome back to the course Sustainability through Green Manufacturing and Applied Approach. So, this is a lab demonstration session. After this session, we'll take you to the Manufacturing Science Lab of IIT Kanpur, where we'll show you the live experiments. How do we do green manufacturing? How do we conduct experiments based on green techniques? This is initial session of that. In this session, we'll tell you about the various instruments that we'll use in the next session, and we'll use this workflow to convert a facility to green. What we'll do, we'll conduct live experiments. Conduct live experiments on unit manufacturing processes. Now, what are unit manufacturing processes? Just recalling, here we have a unit manufacturing process. A single unit or a single machine, that might be milling machine, might be drilling machine, grinding machine, some some modern machine, maybe turning, lathe, anything. Like this is unit manufacturing. It has certain inputs and certain outputs. Inputs are the resources that we use. Outputs are that is the product or maybe some waste. Now, in this case, the input is energy, material, water, and human resource. The personnel or the operator, a skilled operator has to be there to work on this one. And the outputs are goods and bads. I have put word bads here because air emissions, water emissions, solid waste, noise, heat, all these are the bad things which we do not require, but these cannot be eliminated. However, we can control this. So, energy which we have here should be minimized. Minimize energy, right? Maybe some energy might be coming from renewable sources, or maybe lesser carbon footprint, that is the cleaner source of energy if not renewable, right? Then material use should also be minimized. This tool is quite expensive in manufacturing. Tool wear is a basic criteria in manufacturing. Tool wear rate is important to be considered while we do manufacturing specifically in conventional machinings. Now, in this case, this should be minimized. Various other consumables are there. Then we have other resources like water. Water is used in coolant processing. This coolant, this might be, in this case, we use biodegradable coolant. Right? Then is in biodegradable we can use vegetable oil. Right? We have already discussed like ester oil, or maybe some other, we can even add some additives to the mineral oil like molybdenum disulfide, right, to have better results. Then personnel. Regarding personnel, it is important to keep them safe. Safety is the basic concern here, right? Okay. Now we have goods here. Now, if the product that is produced is having lesser impact or maybe equivalent impact than the regular product, that may be called green product. Now, the product, if it use lesser energy or less material waste. Now there are bads that are associated with manufacturing. Air emissions, water emissions, these should be reduced, right? Then noise and heat, we cannot eliminate these, but these can be controlled, right? These solid water, these air emissions, water emissions, noise, heat, and all these solid waste, these also affect the personnel that are working. So these are connected. So besides the long term bad effects, we have also the short term effects to the human operator that those are working on. The noise, that is the sound that is being produced in manufacturing in a machine shop. That is, there are two types of sound we have all discussed. Like it is average sound in the whole day during machining, or it might be the peak sound. These affect the, in the long run, when you work for 5 years, or maybe or some people who are working in machining sector, they work for 35 or 40 years, and in long term hearing impairment might be there, some cardiovascular or some other disease, hypertension is there. These types of bad effects might come. So there are ill effects of these bads in short term and in long term, and also social impact is there. Now when these unit processes are connected together, we have a flow line. We have a flow line. Now in this, a raw material is there, process 1, 2, so on up to process n is done on it, and a finished product is produced. Now these live experiments are conducted on number of processes here. Then each of these processes is separately optimized with respect to greenness. Optimized with respect to greenness. Okay, this optimization might be done based on energy consumption, again, then waste reduction, then one quality parameter has to be there to maintain the quality along with minimizing the bad effects, right? And this optimization might be done with certain tools like response surface methodology, and we have multiple objective optimizations. Then we can even use certain algorithms, genetic algorithm. Then we have ABC, artificial B colony algorithm, then ANN, numerous techniques available, right? Anything we can use. Now once we have obtained the optimum settings, then we have to obviously validate. Right? This validation is done using live experiments again. We validate, or we also obtain the sensitivity. What is the sensitivity of the results that of the factor settings which we have obtained in the previous step. During this validation step, we also conduct time study. Because this processing time, I will go back to this unit manufacturing process again. We have 3 types of times here. Now we are talking about processing and setup time here, right? The setting which is done here is for processing time only. Here we conduct time study, and all these times, waiting time, setup time and processing time, are noted. And we have number of replications here, maybe because this is sensitivity analysis only, about maybe 4 to 10 replications. Now, once we have processing time, then we develop a plant simulation model. We develop a plant simulation model. In IIT Kanpur, we have PLM software. PLM is product lifecycle management software that is provided by Siemens. Also, there are other tools like Arena and certain open source, open access sources are there, like Modelica. Those are available, but PLM is a way good software in that. So this is by Siemens. Then we quantify greenness. We quantify greenness of the factory model. So I thought to introduce all this to you in this phase only, because this is what we are going to do in our lab demonstrations. Now, in conducting live experiments or unit manufacturing processes, various unit processes were chosen. Like in this case, I am showing you a horizontal grinding machine. In this case, grinding machine is chosen. We will conduct experiments on this machine. Regarding this machine, it is a HMT make machine. The model number is here. There is this chuck size over here. The accuracy of the machine is 2 micrometer. That is the minimum depth of cut that we can give here is 2 micrometer. And table speed varies. These are discrete values: 2.5, 5, 10, 15, 20 and 25 meter per minute. And RPM, that is, we also kept RPM same as 1500 RPM here. And the wheel size here was, wheel size is 300 mm, and it is aluminum abrasive wheel, right. So also we did milling and drilling differently, but the machine that was used was this one. This is Amco concept mill 250. So I'll tell you about the machine when we come to the experiments of drilling and milling. Now this is Kistler make piezoelectric dynamometer type 9257A. Now it measures forces in 3 directions: X, Y and Z. In this case, because this dynamometer is mounted horizontally, we have forces that are in this, I would say, I would put this arrow like this. This is normal force. The force in this direction is we call as Fn in case of grinding, and in this direction this is Fy, or in these terms I will call it Ft. This is tangential force and this is normal force, right. And normal force is always greater than tangential force. This mechanical people know, right. I put it, this is Ft. Please don't get confused here. So this dynamometer is calibrated before we do machining. Everything, machine, parameters or every instrument which you use has to be calibrated, because these are experiments and it has to be in controlled environment. So while doing calibration, what we do, we put a belt over here and belt over here and apply a known weight. Right, this weight pushes this machine, or I could say it pulls this machine. For example, if this weight is 5 kg, right? Then we say 50 Newton of force, right? Now when we will go to lab, I will tell you that 1 Newton is converted to 1 volt. This force is converted translated into electrical signal, and we have electrical output over there. And in this case, then we have some correction factors. For example, this 5 kg it has to be 50 Newton, and if the signal is coming maybe 45 or 55, this much error is never there. I will say, okay, if I say, let's say it is like that, 45 or 55 Newton, will put the correction factor in our LabVIEW software. We use LabVIEW software as an interface. This software is an interface between this dynamometer and our computer, right? So we get Ft and Fn both, but this component is enough to tell us what is the force, and this force in turns tell us the energy, or we have chosen this force as a factor that represent the energy that is required to do machining. It is to be noted here, this is not the total energy. The total energy is like this. In machining, this is fixed energy, this is fixed energy, and this is variable energy, and this is only the variable energy, right? And this is, I call it an this is internal energy, okay? And from here we have cord, that is a cord that is connected to our control panel, right? Now in this is a rotary dynamometer. This is another version of this crystalline dynamometer, right? And this is used for our drilling and milling experiments. It is 4 component dynamometer, and it can measure like 4 different components: Fx, Y, Z, and movement also. F in X, F in Y, F in Z direction, and also movement in Z direction, right? So the next instrument is air particle counter. So this is one of the instruments that we have chosen to monitor the workplace environment, right? Out of the bads that are produced, air emissions are there, noise is there, heat is there, right? Now this will count the air particles, what is the size and what is the volume of particles that are present in our machine shop while doing machining, right? Now I will tell you something about air particles. Now there are generally 3 type of air particles, that is inert and viable organic particles, right? Then we have inert inorganic, right? Now inert organic particles come from non-reactive organic material, which is material that is derived from living organisms, right? These come from living organisms, and viable organic particles are capable of living, developing or germinating under favorable conditions, like from bacteria, and like bacteria and fungi are examples of this one. Bacteria and fungi, right? Now what is of our concern is inert inorganic particles here, because in our machine shop we have particles that are produced by rubbing of metals or rubbing of materials with each other. For example, like a carpenter, when he does his work, 2 materials that are non-living are rubbing with each other. In machine shop also we are rubbing the material with each other. With the cutting tool, that is a hard material, is rubbing with or soft material, that is a workpiece, to do the machining. So, right. So, we know that there are three mechanisms: plowing, then sliding, and then cutting in grinding. Plowing is just the material is replaced, nothing happens. Sliding is our grit, the grinding grit that slides over the workpiece, and plowing is just it replaces the material and doesn't remove it completely. Cutting is when actual cutting happens, right? So, but in plowing also and in cutting, the particles, the air particles are produced, right? So, these are inert inorganic particles. Now, humans shed many thousands of inert particles through continuous slowing. For example, dead skin etc. is also kind of inert particles here, but that is not of our concern here. So, we are talking about the particles that are in machine shop. So, regarding size of the particles, the particle size might be from 0.1 to 100 micrometers. Laser 2 model, right, and this has 6 channels of 0.3, 1.0, 2.0, 5.0, 10.0 and 25.0 micrometer. These different sizes are recorded. Number of particles of all these sizes are recorded, right? And particles that are severe to human health are from maybe 0.1 to 10 micrometer that are inhalable. Like that can be inhaled while breathing, and even some reports are there at particle size, if it is even lesser than this one, that even can penetrate lungs. So, regarding the size of the particles, I will tell you some examples regarding, just to give you a certain feel of. Our hair is of 50 micrometer, right, 50 to 150 micrometer, right. Then the particles that are visible to us are visible by naked eye are up to 50 micrometer, right. Okay. Then flu virus is also through the virus particles that are around us in air, and its size is 0.5 micrometer. So, see, I told you, if it is less than 1 micrometer and it is bad for health here. Then pollen is from 7 to 100 micrometer. Then sneeze particles, maybe sneeze particles, right, they are from 10 to 300 micrometer. Then general dust or the regular dust that we have in our playgrounds or maybe in streets is from 0.1 to 100 micrometer. So, this is the size I put here, right, the general size, right. Then bacteria, in this case the particle size from 1 to 10 micrometer, right. So, we have particle size counter here that has these 6 channels and it can count up to. So, what is important to us is, so I will have 2 levels here, PM PM10 and PM1. PM10 is the all the weight of all the particles, like it is weight of particles per cubic meter. So, I will tell you criteria on which this air particle counter is working. So, we have particle, for example, I take a irregular size of particle here. For example, this is a particle, and this case this is I will say longest dimension of the particle, right. This is a longest dimension, right. So, we have some dia that is if I see the other view, there is some dia that I call, that is the average dia of the whole volume, that is known as Farrett's dia, right. And based on this Farrett's dia, we have equivalent area. So, I will draw it dotted. It is equivalent area diameter, right. It is equivalent area diameter, and this diameter is there, that is counted for our particle size here. So, it is giving us this dia, that is if it is 1 micrometer, it is this dia equivalent area diameter, that is 1 micrometer, right. And also because there are certain losses, see the particle counter has certain limitations over it. See the when the principle behind which the principle on which this is working, I will tell you. There is the light, right. There is a light that is passing here, a photodiode is there, that is a light is there, the scattered light is collected by the system, and the particle, this scattered light produced a image here, right. And this image is recorded on a diaphragm, and that image is used to tell us the particle dia. So, when the light is here, it can either diffract, right, or it can reflect back. The refraction might be there, only absorption is the criteria that is used here, internal scattering might be there. So, in general, the researchers have told us that about 67% of the light is like used here, like for actual calculation. So, the particle size what we are having is might be like for example, if we are having particle size of 1 micrometer, right, it is 65% of the actual size. So, it has to be calibrated accordingly, right. So, the principle here is a light source, typically a laser light is used to illuminate the particle, and it passes through the sensor orifice. As the particle passes through the laser light, it scattered or block the light. Right? The scattered light is used to tell us the particle size. Now, next what we have here is sound meter. Two of the instruments here are portable, like that I could bring to this recording room as well. That instrument will show you in the lab demonstration. I have sound meter and our air atomizing nozzle with us. This is our sound meter. I have a power button here, right. Now it switches on. So, before telling you how to use the sound meter, I will tell you something about what is sound and what are various characteristics of that. Now, I will show you a scale. Now, presently we know that the scale that is used for calculating or telling the sound is decibel. Earlier micropascal was used, micropascals, right. That was actually that was sound pressure. This was sound pressure, right. So, 0 decibel is absolute silence. So, even if you enter these silent rooms, you will find at least 15 decibel of sound over there as well. This is my observation. Okay. So, about if you say very quiet room or quiet room, right? If I say it is there is some quiet room, then it is about I would say 25 decibel, right? Then a silent night, okay. This I am talking about the rural night, not the urban traffic. In that case, it is 35 decibel. So while I am speaking during this lecture, this sound recording is, you see, it is about 80 decibels, right? And in a living room, it is about 45 decibels. Okay, I'll take you to the higher sides. Now the 120 decibel is the sound of, I'll give an example of maybe shipyard, right? When you are out on the deck, you will find high sound, right? Or when aircraft taking off, right? And 140 decibel is something when you feel pain in your ears. Okay. Now there are certain other things in between, like a busy restaurant would be about same order as 80 decibels, or a busy office like banks would be of same scale. So certain other things regarding sound, regarding perception of sound. So I'll tell you something about the actual perception of sound. So in this case, if 10 decibel of sound is increased, so what did you guess? What would a human feel? Right? What would a human feel? He'll feel the sound is doubled. And if it is 20 decibel, he'll feel it is quadrupled. Right? So this is perception. So when we have two sound sources emitting equivalent sound, for example, this is 50 and this is 50 decibels, the total sound that is coming up is only 53 decibels, only 3 decibel increase. There are certain calculations behind this one. If you would like to know, we can tell you that as well in the notes. Okay. And the rough rule of thumb for the perception, right? 1 decibel change not noticeable, right? Maybe not at all, right? 3 decibel change is noticeable. 5 decibel, the change is little significant, right? 10 decibel is what? Double. Okay. There are certain parameters like wavelength, frequency, time period for which one is exposed to the sound, right? Then I would write pitch here, pitch, amplitude, right? Then maybe the quality as well. The quality is the only thing, quality. So the quality is the parameter that decide the sound is good or bad, like music is good, otherwise it is noise. Okay. So amplitude is the one that is calculated using our decibel, right? That is represented in decibel. Now the frequency is the number of cycles per second. Frequency is number of cycles per second, and this pitch is actually the brain interprets the frequency in terms of subjective quality, that is known as pitch, right? And this amplitude is nothing but decibels, right? Loudness is an attribute of sound that depends primarily on the pressure amplitude, that is, this tells us the loudness. So next I like to tell you something about the sound meter, which we have used to record the sound while doing machining. So this we have here is X-Tech sound meter. This is SDL 600. So to switch it on, I have to press the power button for 1.5 seconds and it switches on. So in this case, we have this wind, what do you call, this is wind screen. So because the wind blowing over also could disturb. So wind blowing across the microphone increases the noise measurement. So the instrument is always calibrated before doing actual experiments. So high temperature and humidity environments are not recommended for instrument to take along. So this instrument could be used to work in both the frequency weighting scales, that is scale A or C. For scale A is the scale that represent the human ear. So this is even OSHA, that is Occupational Safety and Health Administration. They also recommend scale A to be used to represent the human ear, and scale C is something much flatter, and we even have the options of fast and slow recording, like the sound peaks that are recorded fast in fast mode, and in slow mode it is recorded low. We have max and min modes, and we can keep the backlight on and off, and data hold can be done. I'll tell you how these settings are here, right? So to have max and min, if I press it once, it has started recording. See, REC record rec has come here. Now if I press it again, it has shown the max value that has come since the recording has started. Now if I press it again, it is showing the minimum value. So minimum value will remain same. If I increase my sound, hello, see, the max value would change, right? Okay. Then to change the other settings, I have to go to set. This is for setting date, time, and the data blogging, maybe power off and on, and the scales which we need to do, fast or slow. In this case, because we need to obtain the data at every second, so this data pulse is set to be 1 second, and the recording scale, the recording speed is kept to be fast and on A scale, right? And it has, I'll switch it off to show you the card. This is data logger card, that is recording the data. All the data is recorded in this one, and I'll show you the data in Excel sheet. It gives us the data in CSV format that is easily convertible to Excel, and also this can be connected to PC. This can be connected to computer using this RS232 port, right? This is RS232 port. This is its charging point. Also we have batteries in here, and this is for calibrating, and this may be AC out if required, right? And in data log, I'll tell you the pulse rate that we can that can be put here is from 1 to 3600 seconds. Like after every 1 hour one pulse will be recorded. This much length is required at some places. For example, in some places this is used to monitor the noise for a longer period, maybe for 1 month. For example, traffic in a specific area, right? Or maybe sound in a specific park, in a specific domestic area, right, at specific period of time, a specific for example in evening, right. What they do, the researchers, I have read it somewhere that researcher did research for 6 months to record this sound at one specific traffic point, and differentiate, and they compared between different different weather conditions, right. And they, at that point they set its value, the data the sampling time to be 3600 seconds, right. So this was regarding our sound meter. So the next gadget I have in my hand is air atomizing nozzle, right. This is an air atomizing nozzle that also we call from US only. So generally there are two types of setups for atomizing, like for producing mist. So this system that I am showing here is pressure setup, right. In this case actually air pressure is there, air pressure is also there, and obviously liquid is there, right, and liquid is also supplied through pressure, right. And in this case when high pressures are required, and we need to have like more reach from the nozzle point, like this is a reach, when this length required is much high, then this pressure systems are used. Another system is siphon system, siphon or gravity system, right. In this case the air pressure is here and there is no pressure, but only through gravity we have this mist coming up. Now also we have different type of patterns of flow, right. Now for example this is my spray volume here, like reach of my spray. This might be flat or this might be round, right. This is generally the flat type of pattern is used for painting, etc. And this we have used, actually this hole, this front hole determines the kind of pressure, the type of pattern we need to have. So in this case we have this air cap, this is air cap, fluid cap, and we have 4 holes and an orifice inside. So this is an external mix, the air comes out here, and from these holes the air is coming in, and from this point fluid is coming in, and it mixes externally within this fluid cap. Within this fluid cap it mixes, and we have mist out, right. We can control even the reach, the longest length that the mist can reach using this screw as well, right. So with this I have covered the most instrument that we are going to use in the lab demonstration. So next we will go to the lab and we will conduct experiments out there, then I will tell you how to analyze the data, then further we will go to the next steps, that is factory simulation. Before factory simulation we will even do the optimization of the parameters, and after that we will obtain a green factory. Green factory does not mean that it is all green. Green means that is we have moved a step advance, right? For example, if I categorize into colors from black, gray, maybe blue, then green. If one has moved from gray to blue, that we can say we have turned a little thing to positive side, right? So we'll meet in the lab exam session next. Thank you.